Pioneer brand canola with optimum gly, the highest yielding glyphosate tolerant trait on the market. What's next in canola happens here.
Today on Real Agriculture, we're honored to speak with Dr. Michael Eskin. He's a distinguished professor at the University of Manitoba and a true pioneer in the field of food science. Dr. Eskin's groundbreaking research on canola oil has helped shape the industry into what it is today, with canola now being one of the world's most consumed edible oils. As a newly inducted member of the Canadian Agricultural Hall of Fame, Dr. Eskin joins us to reflect on his incredible career, the impact of his work, and what this recognition means to him and Canadian agriculture. Dr. Eskin, it is great to meet you.
It's my pleasure.
And again, congratulations on being inducted into the 2024 class of the Canadian Agricultural Hall of Fame. That's a big honor.
It is. I'm feel very fortunate.
When you're throughout your career, is this something that you ever thought of at any point, or what was your reaction when you got the phone call?
Well, I mean, I'm originally from England, so I came to Canada in 1968, and it was a really serendipity because at that point the breeders, which would be Downey in Saskatchewan and Stephenson in Manitoba, they were working on rapeseed, and I came to the department. It was then called the Department of Foods and Nutrition, and a wonderful colleague, the late Marion Vasey-Genzer, who was a sensory expert, and she pulled me in to this work. So we worked with the breeders. So I worked in terms of the physicochemical stability, performance, fiber, etc. And my other two colleagues looked more at the nutritional, did the metabolic studies. Yeah. Unfortunately, I'm the last surviving one.
So what drew you to food science originally?
Well, originally I did my PhD in really toxicology. And the story I say is that we, looking at the something called mercapturic acid formation, which is in the liver detoxifies drugs or whatever you take in your body, and they make them less toxic so the kidneys can handle. So I was looking at a series of alkyl halides, some of which have medical properties, and what happens to them. So after sacrificing pigeons, guinea pigs, and rats, I felt that it wasn't the direction I really wanted to go in. So food science was there on the horizon. I had an offer of a position. I'm originally from Birmingham, so I did my PhD at Birmingham. Interestingly, it was under a wonderful woman, the late Sybil James, who was a chemist, and she did her PhD under someone called Norman Howarth, and he actually was a co-discoverer of vitamin C. He got the Nobel Prize in 1937.
Wow.
He was a carbohydrate chemist, and St. Georgi, who identified the extract and did all sorts of studies, didn't have the capability of doing the analysis, so it sent it to Howarth to do the analysis, and Howarth was very famous for the carbohydrate structures, etc. And so he analyzed them, and he got the Nobel Prize in chemistry, and St. Georgi got it in medicine. So maybe it was destined I should move into a more nutritional food-related area. So I decided I really wanted, so I had a job opportunity in London, England, and it was the Department of Food, Biology and Foods, or Food and Biology, at what was then Borough Polytechnic. Now it's known as South Bank University of London. And I saw a job advertised in the New Scientist at the University of Manitoba, and I thought, what the hell, I'll try. But before I knew it, the dean or the faculty came over, interviewed me, and that was in the December of 1967, and they offered me the job in April in 1968, and in August I arrived in Canada. And that's how I ended up at the University of Manitoba.
That's a good time to arrive in Winnipeg. That first winter must have felt a little harsh for you, someone coming from England.
Well, I was someone got me a nose warmer, which I couldn't figure out why you needed that, but that's right. Don't or don't stick your tongue on a lamppost in the winter. That's
rules to live by. Rules to live by. So canola oil is now the third most consumed edible oil worldwide.
Yes.
What do you think are some of the key factors that contributed to that, and where did your research play in its ultimate success and the profile it has now?
Well, I mean, if you remember from the history of canola, the history goes back to rapeseed, when the Polish farmer that came in the 30s, a friend of his sent him some seeds, and they grew very well, and during the Second World War, it turned out that the oil from rapeseed was a wonderful lubricant for marine engines. So they had a growing program in Manitoba to grow rapeseed, and they needed more. So Argentine grows a variety, so they imported. So they had a very extensive program to produce because of the U-boats, etc. So it was very important. And when thankfully the conclusion of the successful conclusion of the Second World War and the introduction of diesel engines, there was no need for rapeseed oil. And that goes back to 45. So someone said, is there any possible use to rapeseed? And it had an awful smell and a color, and it wasn't, didn't seem. And so that's where the work started. It started in Saskatchewan, I think even Alberta, there were people involved. And by the time I came in, it sort of had gone through the development, etc. And it came to the stage where both Downey and Stephenson were doing serious crossbreeding. And they were developing, and they were some novel things that they discovered, and they developed to change an oil that had a fatty acid that was around 50 to 70% in the oil, which is erucic acid, and they changed it and reduced it down to 2%. And at the same time, what they did, with serendipity, that oil had a unique composition. It was very low in saturated fatty acids, 7%. It was very high in oleic acid, C18-1, about 60%. And it had a reasonable amount of linoleic acid, around 20%, and it was unique because it had linolenic acid, omega-3, varying from 8 to 11%, depends on the agronomic conditions. So you had really an oil that had, from a nutritional point of view, low in saturates, and at that time they didn't realize that 18-1 was beneficial, because if you remember years ago, they used to recommend PS ratio for those people who had cholesterol, and the amount of polyunsaturated fatty acids should be at least twice as much as the saturated. Well, first of all, in the canola, saturated was very low anyway, and now we know that monounsaturates are also very beneficial for lowering cholesterol. So you had a perfect oil. You had high oleic, plus you had a perfect match, 2-to-1 between oleic, omega-6, and omega-3. So it really turned out to be very hot, healthy oil, and that soon became, it was identified, and we looked at the stability and performance, and Marion Vasey, the late Marion Vasey Gens and we were commissioned to write a booklet for what was now the Canola Council of Canada, which it morphed from the rapeseed Council of Canada, and to put together all the work that we've done and any other work related to health professionals in the industry around the world to introduce them to this new oil. And it went through, I think, 5 different revisions, and it was translated into Japanese, I think, and French, etc. And so that really helped to establish the oil. And as other people looked at it, it really took off. We had no idea at that time what the impact it would have. But of course, in those days, Canada was the wheat grower,
Right.
and maybe it grew a little bit of corn oil and sunflower oil, but there was no real major edible oil. And so what happened was that essentially the agricultural landscape changed. So now the canola is the largest, from what I understand, contributor of agricultural produce to the Canadian economy of close to $30 billion a year, maybe a little less because of the China problem. Yeah. And it employs over 200,000 people worldwide. So it was really as I said, we had no idea that it really changed.
Yeah. I can remember when we were at 11 million acres and people were like, it'll never get to 15. And now, over 20 is more of the norm. You mentioned 2 names earlier. One is Dr. Stephenson and one is Dr. Downey.
Yes.
Talk about the collaboration with them in those early days, and can you share any memorable moments working with them in those collaborations and how it impacted your research?
Well, it was really quite a nice team. The stories told of Stephenson. He was hired by the Faculty of Agriculture to work on legumes, and but he had an interest to work on canola. On rapeseed at that time. So the story is that he said to the head of his department, he'd also like to play around a little with canola, with rapeseed. So the head of the department said, as long as you do what I expect of you of legumes, you can do anything else. Of course, I understand that he was really ribbed by the canola, by the wheat guys in plant science. They really teased him, and I guess he he had his revenge.
Yeah, no kidding. Yeah, look at me now. Yeah, look at what's happened.
So they provided us with the material, and we worked on the material, and we sort of communicated with them, and so it was a pretty efficient process. And we got to know, and there was a very nice relationship between all of us.
I'm sure it wasn't a smooth ride or smooth path. There was some obstacles and challenges getting to where we are today when it comes to canola. What were some of the significant challenges you faced during the early development of canola oil, and talk about that adversity?
I don't see any real major challenges that took place. There were a lot of interesting discoveries, and there was a lot of excitement, and so that. And as researchers, we were not aware of some of the frustrations when they're dealing with the funding or whatever. We really didn't have. We really had a free hand to do. And remember, this is in the days of bucket chemistry. So, and I love bucket chemistry because now to do any research, you need a $500,000 instrument or $1 million. I mean, the thing that would help in the research on the conversion to rapeseed to canola was the development of gas chromatography. and gas chromatography, the first one got also a Nobel Prize for it. And that enabled very rapid analysis of particularly for when they were developing, they were crossbreeding, they weren't doing any mutations, etc. So they were crossbreeding, and they need to analyze the fatty acid to find out what they had. And there's Helgeson, he, in plant science, let me see, I've forgotten his last name quite a while ago, and he did the analysis, and he was he was crucial, because without that analysis, the breeding could not have taken place, because they wouldn't know what the difference is. So because with the old method of bucket chemistry, it took days to get the fatty acid. But now with gas chromatography, you could get the complete fatty acid analysis in an hour or two once you've extracted, and then it's very fast. And so it was really very without that having to take place, it could not have been done. And I'm just looking for the name here. Fritjof Haugen.
Ah, okay.
Haugen. Yeah, he was the gas chromatography. He was a professor of plant science, and he worked with Stephenson and Dorset County, and he's very often forgotten, and I always like to bring his name up, because without that analysis, things couldn't have moved fast.
Some big that's a good example of some of the big changes that we have in food science. You've been doing this for 5 decades. There's been a lot of change in the world of food science, just like massive leaps.
Well, I think back to the early days, you would apply for a grant for $3,000. I don't think anyone in the States would even bother to lift a pen for that amount.
Yeah.
But interestingly enough, because of the limited, there was really great creativity. Whereas, now, you have all these very sophisticated instruments, and all you have to do is to put the sample in. It does the analysis, and not only does it do the analysis for you, but it does this very sophisticated statistics of thousands of compounds and gives you the raw data. No, that was that was, in those days you wouldn't even dream about something like that.
Yeah, well, putting stuff into, data into a calculator, and all the calculations that you did yourself. Now everything
That's right.
Computer, and
that's right.
There's computers doing the calculations, but AI forecasting of data, like it's
that's right.
mind-boggling.
That's right.
Yeah.
I mean, a good example is that I had some work to do on phytate. I was interested in doing phytic acid in rapeseed, because there was a lot of concern those days, because it chelated metal ions, and like zinc, and so they were worried about if you fed the protein, it would chelate, and you couldn't it would impact the bone. So I wanted to do a study, so I got the grant, but I didn't get the equipment grant. So I got the grant to do the work. So I didn't get the equipment to do the HPLC. So what was I supposed to do? So I had a wonderful technician, and we looked through the literature, and we came across an old paper chromatography method for measuring phosphate esters, which is what really phytate. So, and it was an old method that paper chromatography, you put these to identify, you sprayed something called salicylic acid and ferric chloride, which complex to form a purple color, and any phytate in there because it collated the iron, would create a white color, a blank color. So you'd identify on the chromatography the white spots on the purple background. So we thought that's a great. So what we'll do, we'll develop a method. Instead of measuring an increase in color, we'll measure a decrease in color. And so that's what we did. We took their method, Wade and Morgan, 55 in biochemistry, and we developed this method. And I still get 100+ reprint. It's still used widely because it's a very efficient method, and particularly where they don't have that sophisticated instrument, they can measure it. So that was published in 1980. So that's already 45 years ago, and it's still used quite widely.
Canola has had, quite the journey, as we were talking, from rapeseed to now. What was the attitude of people as you were doing this work and trying to develop canola oil and the profile? And there's one thing to be able to create the product, another thing for food companies to actually use it and procure it and make it a part of their programs. Was there a lot of doubt, or was it more encouragement? What did you sense from stakeholders around you?
I mean, I think the Canadian industry responded very well, and they processed sunflower oil and corn oil, and particularly sunflower oil. So they adapted very rapidly to canola oil. And so I think the industry really started to expand, and particularly with the ready acceptance and the recognition of this was a very good, high quality, nutritional, really heart healthy oil. I think that it really. I don't think that there were many serious obstacles. I mean, I'm sure there were. I mean, it had to be accepted by in the States to. That was a crucial, because if it was accepted by the Food and Drug there, then it was open to the world. So that was the major. Once the oil had been developed, then the challenge was to get it accepted, and that there had to be a whole variety of studies and studies. And once it was passed, then it had that recognition. Then it passed the hurdles. That was the major hurdle.
All of the inductees we've chatted with have talked about the power of the people around them on their team. And we talked about some of the collaborations earlier, but a couple names when I was researching your career: Dr. Bruce McDonald, Professor Marian Vasi-Genser. I'm sure there's others. Talk about the team that you had around you and how that they were such a big part of the groundbreaking results.
Well, I mean, Professor Marian Vasi-Genser was a really remarkable woman. She was a sensory expert, and she did her master's at McGill University. She didn't have a PhD, but in those days, not everyone had a PhD, but she was extraordinarily capable one. And actually, she became the Associate Vice President of Research at the University of Manitoba. She wasn't, there wasn't a vice president, and that was a very high position. And she was, and so her sensory and her statistical, I mean, plus she was wonderful. We worked together for 30 years. Okay. And Bruce McDonald came at the same time that I came, because what happened was it was the faculty or the school I came to was the School of Home Economics. It was part of Faculty of Agriculture and School of Home Economics. And they were looking to separate, okay? And so they hired from McGill, someone called Lou Lloyd, who was an animal scientist, a nutritionist in a sense. And so he came in and he really brought in myself and Bruce MacDonald. He was Lou Lloyd was chair of the Department of Animal Science at McGill, and he came to the University of Manitoba in 1967. And Bruce MacDonald had just started a position there a couple of years ago. He was originally from Alberta, and he did his PhD in Wisconsin, and then he was hired at the University of McGill at Macdonald College, and so he came at the same time I came. And he was so he was a nutritionist, and then with him was Vivian Bruce, who was a local gal she went and did her PhD at Wisconsin also, and the two of them combined. Bruce had the analytical, the biochemical, and Vivian was more, because of her home economics background, had the experience in matching that with food, preparing food and doing metabolic studies. So they were a very good team. And so we all worked together. And the joke is we always knew when they were busy working on a Monday, because they had students on campus that were being fed, and they were analyzing the feces and urine and blood. And of course, we always knew when we came in, when they were analyzing the feces, it had a unique and powerful odor.
That's the ugly part of research right there.
Yes, yeah.
It's not all glory days in the food science. That's for sure. Young researchers, and you've been doing this for, like we talked about, 5 decades. So you have seen a lot of people come in the door, flourish in their careers, people, entering their careers right now. What advice do you give to young scientists and researchers trying to enter the field of food science?
My advice really is that find an area that you are really, really interested, because if you do something you love, it's never an imposition. If you do something that you consider to be an odious task or a necessary task, I mean, there are all parts of research or things you do that you have to do. But overall, I mean, I feel I've been very lucky that I've although canola has been my main area, have been in another number of other areas as well. I was in yellow mustard, and I've also got into some of the more medical related, which is fetal alcohol syndrome. I was associate dean, so I it was a team together, and I pushed nutrition should be important. Now it's essential and that has gone well. And I've done some other interesting things but canola has always been the center. So I've had some wonderful graduate students, postdocs. Sadly, not sadly, I've outlived some of them.
Why is that sad?
And some of them have gone on to have some my first PhD student was Steve Cue, who is at Agriculture Canada in Guelph, and he's just a world-class scientist, done extraordinarily well.
Canola's had a kind of almost come full circle. You talked about it, as a lubricant in the wartime. Now there's a lot of talk about canola oil, not just for food use, but for also fuel as renewable diesel or sustainable aviation fuel. Somebody that's spent a lot of time trying to make canola oil work for food, how does that make you feel if it's going to fuel?
Well, I mean, there are probably some varieties that could be grown specifically that would not be perfectly food that would have fuel. I mean, in addition, I mean, in the period that I've done, we've had a number of challenges with canola. We had in the 80s, we had a problem of sediment formation. And normally canola at cold temperature, whatever, should remain clear. And sunflower, generally, which has a number of it always has a problem because it has components there that give it the haze. And so we had this particular haze, and consumers don't like to see anything floating around in a bottle. And so I had a major grant to look at that and to see what it was, what caused that haze, and how we can get rid of it, and method to predetermine that. So I don't know whether you remember Jim Dawn.
No.
He was head of the grain research labs in the oil section, and sadly he passed away about 5, maybe 8 years ago. And so he was responsible for all these oil seeds, whatever, in growing in Canada, setting standards, etc. So he contacted me. He said, you know what, we've got this particular problem of haze. Yes, I said, I know aware of that. I said, we've done a little work of it, but it's not part of my mandate. Would you mind taking it on? So I said, sure, it looks interesting. So I took it on and I pulled together a team. We got a grant from the NSERC Strategic, and we started looking at what was this. You see what it is in sunflower. You have some gums, and they usually remove them, so you don't get that problem. And it was never a problem in soybean. And so we had to look ways of finding material, identifying what this haze was. And we went, interestingly enough, to a refining factory in Morden that used to be a sunflower, and they used to always have an extra process. It's called to remove this material from sunflower, and they were doing it from canola. So we went in there, we had all this material that we were trying to isolate in the lab. And so we had this material, which was a great help. So what happened was you had this sediment was very long chain fatty acids and fatty alcohols that don't normally appear in canola. And under those certain conditions, they produce this haze. So we had to characterize and then determine a method that we can predict if there is, and it's all related to agronomic conditions when this phenomena occurs. And so this way we did develop a method that we identified what it was. We did all sorts of things, interesting things, and we developed a method to if there's something in the oil, we could precipitate that, and then we could say, okay, you need to do this extra processing step to make sure that you don't get that problem. So that was an interesting problem that caused that. And then I went and looked, then I had a student who was looking for a project to do, and I was on a sabbatical, came back, and they said, can you do anything with her? So I said, I have this interesting. I said, the breeders are all actively involved in reducing the polyunsaturated fatty acids, particularly linolenic, particularly for food, frying, for food stability, and in frying, etc. And they're producing these high oleic and these other oils. I said, and they've never asked the question, well, what happens to the minor components in the oil? And what the minor components, they were antioxidants, in particular vitamin E. And vitamin E is very important because if you remember years ago when they used to add BHA and BHT, maybe not, to products, and the Europeans banned those because they caused cancer in experimental animals. Well, so they eventually banned that and used just the natural vitamin E present in the oil, no additives. And of course, in those days, they used to put oil in brown bottles
Mm.
to prevent the light. Okay. Now the oils are put in
Yeah.
clear containers, which is the worst possible. And and you put them in a supermarket and it's 24/7. They're under the light, right? Well, they hope the turnover is fast. And so anyway, I was just interested. So I said, so I had the gratitude. I said, you know what I want to do, I just want to look, I'm going to get regular canola, high oleic, low linolenic acid canola, high oleic canola, and low linolenic canola. And I also got sunflower and soybean, high oleic, low linolenic soybean, low linolenic, and high oleic sunflower. So we did that. So I said, we want to fry, and what I want to look at is the rate of oxidation and the rate of loss of vitamin E, sorry. And so I got from the breeders and I got all these samples and she worked like a horse, and we got very interesting results, and she was very worried about presenting them because actually the high oleic and the low linolenic proved to be the poorest in terms of stability. The regular canola and the high oleic and low linolenic canola were both best because the other two, the vitamin E was low and it was destroyed fairly quickly during frying. So we got it, and I know we presented that at the American Alchemist Society, and the graduate student was recently married, hadn't had a honeymoon, and she got this award to travel down to Hollywood to Chicago for the conference, so that she took her husband with her, and she presented. And she was very worried about presenting that. And interestingly enough, a paper before her looked at oils, high oleic, regular sunflower oil, and they found the similar results, that the loss of vitamin E. And so what happened was there was a lot of interest to how can we determine the stability of the oil, particularly at the breeder level. And so we had to look for a method, and we used a method called the the name. It's a method, thin layer chromatography, but you do it. You can take just micrograms of the oil and separate it. And so we were able to develop that method. If I can remember what I must be my age, I'm forgetting it. It's Atroscan. That was the name of the instrument.
Okay.
The Atroscan. It was based on thin layer chromatography, and it was really very fast. And so we were able to use that to show the having a rapid method of looking. So why was it rapid? Because you could put the sample of the oil, and you could put it in a tank. You could put it in. You could warm it up, use a temperature, and then once you take it out, you could then separate the components and see how much oxidative compounds are produced, and you were able to measure that very quickly. So you could see that the oils that were more stable, they produced less oxidation during the heating storage. So it was a very rapid method, and we presented. We got an outstanding paper award on that, and we published that. So there's a lot of so that was in what we did on the oil. In the more recent years, I've been looking at the meal as well. In the meal, of course, there are a lot of canola is very rich in phenolics. It's extremely rich in phenolic compounds. And many of those phenolic compounds are powerful antioxidants. Some of them have anti-cancer properties, etc. So there's an interest now in looking at natural materials. There's the old joke of a man sees his doctor, and the doctor gives him a prescription. He comes out with the prescription. He goes to his pharmacist, and he says to the pharmacist, "Tell me, on this prescription, what's the first?" He said, "Oh, the first is a particular medicine to deal with the condition you have." I said, "Right." He said, "But what's the one next to it?" He said, "Well, unfortunately, that medicine has very nasty side effects, so you need to take that." He said, "Okay, but what about the third one?" He said, "Well, the fourth one, the fifth one, the sixth, go through this 10, all that." So he turns to the pharmacist. He said, "Tell me, in your professional opinion, what would you recommend?" He said, "Personally, I think you're better off with the disease." So, I mean, cute. Anyway, so, I mean, essentially what now is looking in is dysfunctional foods you've heard of. In other words, foods have an additional to their nutrients, their components or phytochemicals that have strong antioxidant, anti-cancer, all sorts of properties. So in canola in the 2000 in Japan, in the processing, and they noticed the production of an interesting phenolic compound, which is called canola. Canola, because it's canola. And canola is not found naturally in canola. It's produced in the process from synapine, which is the largest synaptic acid and choline, and it's very high. And what happens is in that process, synapine loses the choline, becomes synaptic acid, and then synaptic acid rearranges itself, loses carbon dioxide, becomes canola. And canola has been shown to be we've looked at a lot of work on effective antioxidants, and other people have shown it to be a strong anti-cancer compound. So we've been looking at ways to accelerate that process. If we can extract and put heat on and microwave, we've done even air frying to take that material and produce more canola. And it's also present in yellow mustard that we've done that with, and it's also present in some other compounds as well, but it's particularly rich in canola.
So, last question. All inductees into the Canadian Agricultural Hall of Fame, they paint a portrait of them, and it's pretty cool. What's your thought? What goes through your mind, do you think, when you see that portrait for the first time?
Reminds me of the joke, I need to go in and have a photo for some event. And so I said, I'd like to have that young, handsome look of what's that actor who not so handsome now in the late 80s. And he said no. And he mentioned another rather characteristic comedian. He said, "We're doing this character this week." So I said, "I guess I'm going to have to be happy with what I can get." I haven't seen that portrait.
Well, it's coming soon. Dr. Eskin, I want to congratulate you on a tremendous career that is still going, I might add. You are still at work, and your contribution to the world of not only Canadian agriculture, but the globe is amazing and outstanding, and I really appreciate you sharing your story with us here today. Thank you so much.
My pleasure. Thank you.